Alright, hell yeah. So what we're going to do, or what I want to do, is disprove the mold effect. And let's just do it. Like, let's say you were biking and you're like, bikes are balanced. Is that because of trail? I would say no, that is not the fundamental reason why a bike is balanced. You can have plenty balanced bikes. You might not be able to ghost ride them. But you can have opposite tree. You can just take that totally out of the equation. So every problem kind of has its roots. And so we're going to do the ball chain fountain. You know what I mean? It's this little thing. You got two balls, and they're connected. And the idea is that one is getting kicked up. And because you have the center of mass. Now there's a lot of this I will agree with. But let's just set that aside. And let's go through. So this first, just a couple analogies right here. So I have this pile of rope. I ain't going to take it all out, but you see it. And now let's say like right here, I'm going to pull on this pile of rope like at 5 miles an hour. Okay, let's say I did that. Well, why isn't this rope right here, why isn't this rope right here going 5 miles an hour? Let's do it again. You know what I mean? What the hell? Like, well, I think that's pretty obvious. And then, you know, to get you up to speed, let's say this was around a track. You know what I mean? You put this whole rope either around a big circle, around a building, around just one tree, and it's all taut. Hell yeah. You pull on this rope 5 miles an hour. The whole thing's going 5 miles an hour. But what we have with the chain fountain is you have rope that's not moving and then rope that is moving. So yes, if I do pull this 5 miles an hour, yeah, like right here did not move, but guess what? Right here was going 5 miles an hour, right here didn't move. So we have a velocity gradient. We have portions of this that are picking up speed. And the only way that's going to happen is if they kind of change the path, having the path allowed to be changed. Okay, now let's just get into my declaration of what the mold effect truly is. This is the best representation, and it's so simple. So what we're going to do, it's still hypothetical, so then we got to go through a lot to, anyway, let's do it. So you got a ceiling. Okay, fair enough. And you got like, we're talking like a pool ball. Whatever the weight of these are, you got one pool ball. All right, fair enough. Guess what? On deck, you have some string, and then you have a second pool ball. Okay, we're just going to ignore that second pool ball for a second. But we're going to drop this first pool ball. So pretty soon this first pool ball is going to be right here. Wouldn't you agree? I think so. Alright, so this first pool ball, its velocity is 0 up here. We're just going to say that's initial velocity. Right here, we're just going to call that velocity final. People do that. We're just going to say it's some sort of constant times its mass times gravity. You know what I mean? It's basically a function of gravity. That's it. Gravity is causing it, like the G is change in velocity, change in time. That's 9.8. Okay? I'm just throwing the K in there just as a constant, you know what I mean? Because you never know. It might be just a little bit different. Alright, so hell yeah, let's get pool ball 1 down here. But as pool ball 1 falls right here, now this is sleight of hand. This pool ball 2 on deck, we're just going to push it over here. You know what I mean? We're just going to take our hand and then just kind of give it a little scoot. So there's pool ball number 2. And like I said, it was attached to a string, just a real loose string. But now this string's totally taut. And we have an impact. There's no difference between a pool ball coming in with a lot of speed, hitting another pool ball. Well, what happens? This pool ball might dead stop. And then this pool ball continues with whatever speed was going. Okay. Alright, kind of a suggestive drawing down there. Anyway, let's get back to it. So you're going to have an impact. And it doesn't matter if the pool ball is this way, or if this is pool ball number 2, you have a string like this, but then you roll it taut, and then you get this up to speed. So this speed is 0, then you got this speed from here, you rolled it, You got it up to speed as v final. Well, guess what? You're going to have an impact where this will have no velocity, but then this will. So I think that is super straightforward, because that's the MOULD, is the MOULD effect. You have collisions. So anyway, this velocity is going to collide, and then all of a sudden, this velocity does go to 0. So I'm just going to indicate that. But then, hell yeah, what happens to this? What happens to velocity of number 2? Velocity of number 2 has this, kmg. Now, this is where the magic happens. You're just like, whoa. If you recall from before, our initial setup with our initial pool ball, you drop it, you have to drop it from 0 velocity. So yeah, gravity does a pretty good job, and it gets up to speed. But if you already have something with an initial velocity, holy Toledo. By the time it would get to the same location, it's going to be much faster. Okay, so let's do that one. So now we're going to have number 3 on deck. And so number 3 is going to get here. Number 2 is going to get to the top position. Now this is where you might be like, well, isn't number 2 going to run into number 1? And I might be totally wrong. This is where it's kind of hard to rack your brain. But I don't think so. I think categorically number 1, and it's because of yes. Okay. Yeah. Because this is why so after 1 gets impacted, 2 flies towards number 1, and it's got to travel this distance. But as it's traveling this distance, this thing's moving a little farther. So yeah. So by the time 2 physically in space gets to this position, number 1 for sure has to be down here. So this is the proof. And if number 2 gets to this position, guess what we just did? We just pushed over number 3. And then number 2 and number 3 are going to get taught, because that's the only distance you can travel before these get taught. And if you're like, what the hell are you doing with balls? And then making this video so suggestive. It's because ball chains, we're just going to make this worse. You have 2 little holes, and then you have like a rod that connects them. And then so see how this rod can actually go a little bit farther apart. These balls can actually go that far apart. Oh, now this video is just X-rated. Okay, or these balls can be close together, and this rod can be all the way through. So, ball chain, don't want to say that 10 times, but anyway, has this property where you can actually have collisions this way, and collisions in this direction, and collisions in this direction. Okay, I think we got it. Okay, but I just proved that number 2 is going to hit number 3 before 2 collides with 1. Because well, let's just do it, because this is the magic. So what was velocity? What was the velocity of 2? Well, it was kmg. So this right here now is kmg plus another, k prime mg. You know what I mean? It's almost like, it's almost twice the velocity. I think it's just twice the velocity. Hard to say. But okay, once this impacts, this velocity goes away. So it's 0. And guess what? This was hella now, because now this is that k mg plus k prime mg. It's kind of that your initial velocity is just now huge. So that's impressive. Okay. And this is theoretically, we're just saying, hey, this next one we just push into place. Number 4 is on deck. But you can see this process. If I had balls on the ceiling and I just dropped them and they were attached to a rope, and then I kind of just slid the next one and then just let go at the just precise moment it was going to impact, it's going to yank that one. You're gonna get this slack happening. So yes, and by the time the 4th ball, these are going to hit, and yes, you do lose. Whatever you gained here, because this one is still this one is still k prime mg, because it got hit right at this initial So anyway, so after 4 gets in place and 3 gets down here, for sure you're gonna have a collision between 2 and 1, and then once these things collide, you know what I mean, you're gonna lose what you gained. All right, I have to take a step back, but 2 is gonna get down here before 2 hits 1. You know what I mean? 2 is gonna pull on 3, have that impact, gonna make this go hella fast. So this is gonna be velocity is just gonna be that. Whatever this was, which was kmg plus, we're just going to call it k prime mg, just 2, and that's this, kmg plus k prime mg. So it's 2 of them. But then at some point, 2 is going to hit 1, and it's going to lose what 1 gained, which was this kmg. So that's going to go away, and you're just going to have this residual, and that's going to be like normal. But what I want to show is that with a ball fountain, you have another property of once the chain actually hits the ground. I think we all know this, and we want to know why. The whole thing just takes off. You're like, what the hell? And then so this explains that. And yeah. And I think you can see like once number 1 came to here and then transferred all its velocity to number 2, sure, but this has no velocity now. You know what I mean? The second 2 hits 1, you're going to have that same, whatever the change in, oh, and then, so this is interesting. So once 1 impacts 2, this has 0 velocity, this has got hella, but then they're both, so the change in velocity between these is just this, it's just that hella. Okay, it's always going to remain that hella because gravity is just 9.8. So the that's change in velocity. So the change in velocity is only 9.8, and it's going to happen to both of them at the same time. So now when these two are in free fall, their velocity is going to change at the same 9.8 for every second that these are in free fall. But they will collide because you do have this change in velocity. And then once they do collide, down here, let's say it happens right here. Just for, it doesn't. We proved that it's not going to happen before 2 impacts 3 to get this extra juice. But let's say it does. Whatever 2 had, it's going to lose. So then 2 just goes to 0. And then, you know, then this drops. And, you know, irregardless of, so, and then if you let go, so if 2 lost all its velocity, and then 1 started going on a path, and then you had to let go of this, at that moment, this still has velocity 0. Okay, so what I propose with the chain fountain, after it hits the friggin' ground, is this. Pretend like this almost impacts, but then this hits the ground. And then once this hits the ground, let's just say, you know, this magic hand removes it from the equation. You know what I mean? Now it's over here. Now it's gone. So now it can't impact, you know, it can't slow this one down. This one keeps its velocity. And even with just 3, with a ball chain of just 3 of these, it shows that this gets to keep all this, and by the time 3 hits 2, so once 3 gets here, it's going to have this, the velocity is going to be, and then it's going to be plus the mg that it's going to free fall. So then you have another k double prime mg. So that's complicated. I'll get better at explaining it, but hell yeah, even right here, I think you get this. The second you drop this ball, it's got some velocity. It's going to impact and transfer all that velocity up here, and then so you have an initial velocity. This one you just drop free fall. It has 0 velocity at the start, but now this one you're kind of throwing down at an initial velocity. And by the time this gets to here, again, it's going to impact number 3 with this velocity plus mg because it's falling through the air to get to. This is falling through the air to get that k prime mg, and so now 2's down here with k prime mg, and it's going to impact number 3. So now you're going to have that, And if you take 1 out of the equation because it hit the ground, then this, by the time 3 gets down here, is going to have K double prime mg. So those are the, just using 3 balls in the ball chain, by putting them in place, you know, then this has nothing to do, so I'm done with this. Now, it has nothing to do with the fact that, you know, these are, you know, the center of mass is here, and if this gets pulled down, but sure, we can do the same thing. If this is 1 and this is 2, and then this is going to be 1 down here and this is going to be 2, by the time it swings down here, you know what I mean, you kind of have your impact. And but it's ball chain, so by the time 2 gets down to here, and then you got like another one, 3 over here, and you switch places with that, so this becomes 4 and 3, and we're done with 1. 1 isn't going to be at full length because these it already impacted, and it's going to be a little shorter. So that means its rod goes through these balls like that, and then you can do that same. And then this can now swing down and stuff like that. Alright, so, alright, hell yeah. Now this is loud as, but this shows that you don't have to have a chain to actually get something to elevate. Now we're just going to do constant velocity with this, and it's going to hop and skip. You know what I mean? And the second it hops, like this thing has weight, but it has so much velocity. Hey, let's just do it. Alright, so there you go. So it skips and pops. Alright, hell yeah. Let's see if I can do this train one. It's a little different than the ball chain fountain, because we got to go back to the ball chain. Here's train car, oh shoot. We need to at least get 3 of these in here. I'm not helping myself out. Alright, train car 1, train car 2, train car 3. Alright, so 1's going to hit 2. But it hasn't hit 3. Train car 1 is the only one with an engine. It's the only one that can have force. Okay, fair enough. These 2 are just rolling. We can get that. So 1, because okay, this started off with 0 velocity, and it had force, you know, of some sort, so it's got some velocity here. We'll just say V final. And guess what? Once it impacts, this thing's got 0, and this has got V final. Okay, and then so scenario number 3, 2 and 3 hit, and this doesn't have an engine. 2 does not have an engine on it. It didn't have that mg, it didn't have that K prime mg, because there's no gravity here. There's no just extra force that's trying to attract this to that way. You know what I mean? And so, so it's just got this initial velocity. Has no acceleration, so its velocity doesn't change, but it still runs into it because this 3 over here, this is 0. That velocity is 0. Okay, so these 2 hit. Now the question is our train car 1 still in the same position because it had 0 velocity? Hell no. Hell no, because it's an engine. It's constant force. So, so hell yeah. So now it's going to be slightly closer over here. And because, and then here's the crazy thing, is there's no way, unless it's a perfectly smushy impact, where this train car just instantly smushes into car number 2, and then these are just 1 unit, fair enough. The velocity will slow down, but then this force will drive it into that. But what we're going to say, it's totally like two pool balls. It's going to transfer. This thing's going to go dead stop just for a second. It's going to transfer all its velocity. But this thing's got another force. So it's just like it started here. This thing has 0 velocity and then starts to move. Same thing. Again, it has the engine totally came to a dead stop, but now it's starting to move from this position. And this velocity is 0. This velocity has some, so you're going to get a separation. You know what I mean? And so by the time this hits, so you are going, this is going to impact this before this reaches, before the first engine reaches car 2. And then so on. And, you know what I mean? Even this transferring its velocity might happen 3 might hit car 4, like I said, before 1 impacts car 3 and 4, because 1's going to impact 2 again, and then those are going to impact. But you can only do 1, 2, you only can do like 3 things before this just becomes like a, you know, an amoeba of force, you know what I mean? You're doing waves of force, waves of changing velocity in the system. And maybe that's totally wrong. Maybe you can have a train and just, I don't think so. You know, smush all the cars together just in one loud crunch, and then they're all going, you know what I mean? Maybe this is just crazy high, this force that's just crushing them all together. But more likely, this is the scenario. Even at a molecular level, you're having impacts, you know, back and forth. Okay. All right, hell yeah. All right, so the mold effect is a bend radius problem. So we live on Earth, and guess what? If the Earth is spinning this way, you know what I mean? Because the North Pole's here. Man, I got to make this video more family friendly. Okay, so the North Pole's up here, and anyway, guess what? Guess what? You want to fly off this thing. If the Earth's spinning like this, North Pole's up here. I know the South Pole's like way down there. You know what I mean? You get it. We're looking at this direction. But you actually want to fly off at the equator. If you want to fly off at the equator, doesn't that mean you weigh less? Hell yeah. So you have an mg. The other force in physics is this normal force. And then you have this omega, which is just the rotational speed of the Earth. Now, this is what you need to do. Sum of the forces equals ma, and then you got to be like, okay, mg is down, so we have negative. Oh, did I even? Oh, well, we're saying mg is the positive direction. You know what I mean? Because you weigh, let's say, I don't know, I weigh 160 pounds. Okay, perfect. So we're saying mg positive. This is the positive direction. Minus what the scale reads is equal to the mass times acceleration. Well, if you're on the North Pole, there is none. You know, this goes to 0 and you just weigh what you do, nice and heavy. But if you go to the equator, hell yeah, you can weigh like 8 ounces less. Because your mass times your acceleration is in the radial direction, which this is the center, so that's the radial direction. And your acceleration, the radial direction, is negative omega r squared. So it's due to that speed. So then this is, and it's just maybe negative r, no, I like it that way. So, alright, holy Toledo, ran out of juice. And, but this one, the sign conventions are just kind of all over the place. But, I mean, you sum the forces and then you do the ma, and your a is this negative omega r squared. But, I don't know. It's like a centrifugal force. So, but anyway, your scale is going to read this. Newtons is equal to your weight, like 160 pounds, minus omega r squared. Which this might be like 2 pounds. It's not. It's like 8 ounces. But hell yeah, fly to the equator. That's a good diet plan. Weigh 8 ounces less. You know what I mean? You can splurge. But when you get back to the North Pole, you're gonna wish you didn't gain that 8 ounces. Anyway, all right. So that's how things want to fly off. And yes, you do weigh less, but I think the take-home point is that's why the sign convention is always interesting, because like basically this thing's spinning, and I guess it's this way. You know what I mean? But you're flying this way at a huge velocity, and technically you should just be going straight. You should be right there. The force that it takes in this direction, that force that actually puts your feet onto the Earth because it's spinning and the Earth wants to merry-go-round you into outer space, it's this distance. And because you have to get back to this distance in a certain time, you know what I mean, change in distance, change in time, well, that's velocity. And because you had velocity 0 here, but then you'll have to have some sort of velocity average to do that thing, well, hell yeah. You just have change in velocity. And that's literally the definition of acceleration. So you do have acceleration, and that acceleration is in the radial direction, negative r, Oh, I totally messed up. It's negative r omega squared. Yeah. Holy Toledo. It's not r. Yeah, it's r omega squared. That's why. Anyway, but that would be. It takes about 8 ounces. It takes 2 pounds. Is it 2 pounds or 8 ounces? I forget. Let's just say it's 2 pounds. It takes 2 pounds of force to actually keep your feet onto the earth. So if you had the anyway, all right. So we got to move on from that. But when we do, why is that important? Because here's our chain fountain, and look at this. You have a radius. You know what I mean? So right here, no radius, no radius. Right here, no radius. But right here, hell yeah. So you have this radius. So you have these little pieces of mass, and like this mass, again, you know how I was just doing that person? You know, the person wants to be over here. It don't want to go around this merry-go-round that you decided it wanted to go on. And so theoretically, the mold effect should just be, you know what I mean? I mean, it should be more. You know, it should be more. You initiated a huge velocity here, v max, and then it's got to do this tight radius. Well, and then the tighter the radius, well, maybe those two, but you have a constant velocity, and yeah, because your acceleration is your r omega squared. So your force, you know, we want to know a lifting force. That's what we're trying to get. We're trying to get a force that lifts this friggin' chain up. Well, force is mass times acceleration. So you have the mass of these little balls, r omega squared, and these balls do want to fly off. These balls want to be just like these people. They don't want to do this circle. They don't. They want to fly off in all directions. Well, the radial directions. And because they do, they're going to have a lifting force. And yes, if this radius is smaller, this force is less. Okay, but guess what? If this radius gets small, this omega goes to it multiplies by 4. Actually, if this radius is bigger, your radial this actually goes down, because this circle can either grow big or it can be small, whether you got the chain out of the fountain like this or the chain out of the fountain like that. And so just looking at it real briefly, hell yeah. The smaller the radius, it's going to be way harder. These balls do not want to do a tight radius. Like, you just keep making this radius tinier, hell no. They're going to go super high. So if you notice that the radius, so I'm going to say this is the first observational thing I can say from science, is that if you notice that this radius between here and here gets smaller, and then this radius gets smaller, you're going to have a taller fountain. If this radius widens out, you're going to have a lower fountain. It's because of this. This is squared. And this, yes, if you lower the radius, it lowers the force. But you increase this by a multiple of 4. Because you're changing the circle. You know what I mean? Alright, so that'll be cool. Alright, hell yeah. I think that was the best point right there. That was actually, this sets up a good deal. And I know I'm a nobody, you know what I mean, but I challenge some of these, you know what I mean, the 26 million view, you know what I mean, scientists on YouTube. It's so easy for them to just do subject after subject, but to actually set up, challenge me. Well, let's rehash this thing. I know, like, it was 5 years ago, and then it was last year. You already did your rebuttal. I just missed that video, and it's just like, hell no. So I still say no to this, no to the mold effect. All right, and let's see if there's anything more I want to explain. Well, I guess just this, and I think there's 2 more. But yeah, we were talking about a narrow radius. Well, why would this radius go small? Why would you have like a small radius right here? Well, look at all this weight, you know what I mean? And this is fixed, you know, so So because all this weight pulls down, it's going to pull this radius, but you do have velocity, and this radius gets small, so you're going to get extra height. So that's that in a nutshell. But it still goes back to, well, let's do it right here. Because you're like, how do you put all these pieces together? Well, because you were talking about dropping a ball. You do have gravity, right? So you got G, 9.8. This ball is going to be right here. Then you shove over another ball. And then you impact this. This velocity goes to 0. This velocity goes to hella. It's V1. V1 used to be just 0. This used to be 0, right? And but now you got V1. Okay, and then you keep doing that. Now you got 3 up here, 2 right here impacts, and then 1, like we said, 2 and 1 didn't hit. And then you got 4 on deck that you're just magically shoving into place. But they're all on a ceiling. You know, that's an important thing. Because I tried this as a test. I tried to just drop 2 chains. I did ball chain like this, and then ball chain like this. So I had to actually put this into a cylinder, and then drop it, and it fell out of the cylinder. And then I did a ball chain like this. And then I dropped, so they both have the same kind of starting heights. And then when I dropped them, I don't have high-speed cameras, and actually it was the same. They hit the ground at the same time. Because if you're just dropping this whole unit, and it's all influenced by gravity, then everything starts at 0 velocity, and then starts to go by gravity. But what you have here and then this is totally related to the ball chain, and let's get to it. Because the ball chain is a container with a ball on the bottom, 1, that's getting pulled up, and then the next ball, I'm actually going to call this one 1, and this one 2. And then just theoretically, you induced some velocity in the system. So this 1 already has velocity, and is going to impact number 2. And so once it does, this part of the chain is going to slow down. And then number 2 is actually going to get kicked up. So that is the kicking up force that I would say. The same force right here. I think you totally agreed with me. We'll probably have to do a little bit more work on this, but when 2 is right here and 1's right here, 2 is going to go in. 2 is going to have a high velocity. This velocity is going to go to 0. So right here, this velocity is going to slow down at least, and this velocity is going to go higher. This velocity. So let's say this is your V max. It's just your ball chain can only go so. It can only have it basically reaches a steady state where you do have you hit a V max, and then so when you impact this first ball with V max, this whole system slows down just a little, not much, but then this ball right here goes a lot faster, and it allows you're putting more energy into the system. Just like right here. And, man, I guess this is where you just throw in the towel, because it's kind of hard to, it's hard to just totally, be like, oh, that's exactly what's going on, because you're just like, well, what the hell, gravity's going this way. But it technically doesn't matter, because this is your gravity component. Your gravity is pulling on this. This is just a bend in the system, and then you're ending it on a ceiling. So the ceiling analogy worked really good right here, but you're just putting the ceiling right here, just right at the end of this bend, and then so you have all those effects in play. So in conclusion, all right, hell yeah. So in conclusion, I believe that the most important aspect of a ball chain fountain is having the balls 1, 2, or whatever, a 2, 1. I guess we're going to do that. 1, 2 on the and then having them be able to do this, you know, on their rods. Having one be able to get up to Vmax, and then instantly, because right here, the velocity of this one on the bottom of the container is 0. But then once you actually get it up to Vmax, you impact this one. So see how this one was 0? So it takes actually a lot of energy to get this one up to Vmax. But now this is already, now you're impacting this one, and this one gets impacted to Vmax. Damn it. It just doesn't feel right. Doesn't feel right. I agree. I totally agree. But this is the best. This is the best and simplest way I can feel it out. You know what I mean? It's complex, but so anyway, even though it's upside down, I think, because this is the way to look at it, I think it's better that these two balls can do this and impact than kind of the mold effect being like, well, this ball is being pulled up, and when it does get pulled up, it's applying a kicking force, you know, some sort of kicking force. I do agree that this is better than a rope. Like just the fact that a rope can like bend. I do like the pivot of a ball chain, like having a pendulum, because this goes to here and pendulums up. It allows that. It's the same concept of this going to this. It's building energy for a strike, and then it strikes and impacts it, and then this gets hella velocity. So even with the pendulum, I believe it's more of a pendulum up to here. It's not the ideal. The ideal is to have the balls just like this, stack them just like this, and have them impact, and then keep impacting like a train. But you can't have a train and then keep magically putting the balls in the same location. So that's just by chance. You know, the ball chains, as they're fitting like this, they are in this position, and you are able to pendulum. So I would say it's the pendulum aspect of a ball chain that simulates this to this, and then a striking impact. So this pendulum provides, because look at this, when this goes to here, so this velocity is 0. If this velocity has some component, oh, this is perfect. All right. So this sums up my argument for what I would challenge the mold effect. And why this design is nice. Like I said, this design is way the hell better. You know what I mean? This to that. That's way better. And we'll just put it, we'll just put this here. Initial to that. And then you have a strike. So how do you get a strike here? Well, when this thing goes on a pendulum up to here, guess what? The velocity is 0 right here. Velocity right here is max. You know, V max. But when this gets to V max, this is still V0. See, where a rope wouldn't do that. A rope, the second you, even if the rope's like a, let's say you just have like a chunk, so you have a rope that's real short, and that's the rope resting, and then you're going to pull up on a piece of rope. I think it's just already going to lift off the surface. If you're looking at this lifting off the surface, it's going to happen a lot faster on a rope, pulling a rope up. And this is the rope, so you're pulling the rope up. This is going to detach from the surface, where this acts as a pendulum. So this ball does not have to leave the surface until the greatest moment of impact. And then you get a strike, and then this ball can have just an impact of energy. So this ball initial will actually have a V max, but times a constant. It'll be a little bit lower. So just V normal, yeah, V min. But at least, even if it's V min, even if this, once this gets to here, this has a V min as an impact, then you're already, you know, you're already doing what this diagram does. Okay, and I think I can conclude, it's good to conclude right where you started, because you have this rope. You have, you know what I mean? So I got it all piled up in the ball chain. I'm pulling this 5 miles an hour. Why isn't this piece going 5 miles an hour? You know, there it started to move. So, you know what I mean? When I was pulling this 5 miles an hour, this just started to move. This was 0 velocity. So there's your velocity gradient. But that's I think yeah, I'm trying to figure out how to, you know, like in the ball chain, you can say all this is constant velocity until about, and then even right here, because I even made a video on this, and if you go slow-mo, these little sections, they have bursts of velocity. They have bursts of velocity and then bursts of no velocity. And until those kind of peter out, and then you just have constant Vmax, and that's your driving force. But the fact that the velocity of all this chain is 0, you, I mean, this is the force that Steve Mould, you know, force is just mass times acceleration. And what the hell's accelerate? Mass times change in velocity. Yeah, you have all these little pieces of mass. And guess what? Until they actually get to here, you have changed their velocity. They have mass, so you have a force. And that force is going to be felt on a scale. So that's why Steve Mould read like 0.3 newtons. Little Taco Bell. Little Taco Bell taco. You know what I mean? It was the weight of a meter of ball chain. Like that it's either 1 foot or a meter of ball chain. That was pretty impressive. And that's the amount of ball chain in this loop. So here's your mg right there. But just the driving mechanism, you know what I mean? The whole idea of just something kicking up, you know, it's like, yes, you put a scale to it, but it didn't mean there's magical jumping beans. But I mean, I do, like, there is some physical properties of this that are great, because you do have a center of mass right here. So it's real easy to rotate this. And when you do, when you bring this velocity up, it goes real easy because it's not influencing on this. You're not pulling twice the mass, and your center of mass doesn't have to go. When this gets the hell up here, your center of mass only had to move a little bit. So this is where you get that strike, because until this gets to be like vertical and your center of mass is here, then it's going full. You know what I mean? So between here and here is just such a nothing burger of the center of mass, and until you have this moment of jerk and strike, and then you can jump from here to there. So that jump's going to be your impact. This jump is going to be your, you know what I mean, double pump on the trampoline. You know what I mean? So yes, this is double pump on the trampoline. Do I need to add more time on the clock? But even 4 years ago, you know what I mean, the original question was, why does macaroni, you know what I mean, why the hell does macaroni work? And what I would say is it's the ability. I would first do this, you know what I mean, draw the macaroni here, and then put it on a string, and then draw the second macaroni. This is 1, this is 2, velocity Vmax. Velocity 0, impact, this goes to Vmax, this goes to 0, but like I said, you can put 2 and 3 here, do the same, and then you can get another one before 1 and 2 ever collide, and again, take it home. If this hits the ground, then the magic happens because you took this one out of the system. So whatever you gained in number 2 and number 3, well, whatever you gained in number 2 from that first impact, you will not lose, because 2 will never hit 1 if 1 can hit the ground. Now that's the simple, that's 1, 2, 3 of these. That'd be the shortest chain fountain in the world. But I think we started, went somewhere, brought it home, and I think this really shows. So yes, what would be the... And it's unfair that the best ball chain is just ball chain. You know what I mean? You can't make a better ball chain because these do have mass, but they're real light, and you know what I mean? So just extra heaviness and friction and drag and all, inertia, you know what I mean? So you can have a ball chain that just flies up because you're doing a small radius, and you have a driving force of a big mg. That's why you can throw this off of a deck. Yeah, 3-story deck, hell yeah, you can make a big mold effect. Right here, you know what I mean, is your ceiling. Right here is your ceiling. Let's do that. I think we can take that home. I think we can make that make sense. So yeah, here's your cup, and then here's your big mold effect. But here's a 3-story deck. You know what I mean? And the fact that this right here, these balls are just zero velocity, and then instantly Vmax. Like I said, there's a lot of collisions in here that get them up to Vmax, but essentially impacts that are driving this. And then so that there's no reason that this just can't be right here. You know what I mean? Take this up to here, we'll leave this here, drop your thing right there, and you're having stationary balls in here. These are Vmax. I mean, these are V0s. These are all these balls in here are just zero velocity. So then you have this magic where you dropped 1, and then 2 is just magically there. And then once 2 gets to here, and 1 hasn't been impacted, 3 just gets hella magically impacted in huge velocity jump. And then you do it again in 4. But these balls are just magically showing up, and they're magically attached to the ceiling. That's why I do want to try to do this in diagram or an example or something. But it's just real hard to actually like stick washers or something to a ceiling. Like you could do it like dominoes, double-sided tape, and just barely hang washers just with double-sided tape. So the second one washer gets down to here and jerks on this washer, you know, it would pendulum. You know, you wouldn't have to have it, but then this theoretically, if you drop this washer and it pulled all these, should theoretically drop before dropping just a normal washer at the same time. So this is cool because it shows why the mold effect works, and it shows that Vertasium of dropping a chain, so he's got a chain connected right there. He's dropping this at the same time as dropping a rock. Or, you know what I mean, another person drops a rock. Here's the ground, and they're up on a concrete thing. And this chain will hit the ground first before this rock. You know, there'll be a discrepancy. And this shows that mold effect from the ceiling, and how this cup of chain fountain is just the ceiling. You know what I mean? Your cup's on the ceiling, and you're doing the same thing. You're pulling the chain fountain. You're just whipping it through that circle of small radius, and these masses aren't very small, but your force of acceleration, let's do that, it's m r omega squared in the negative direction. In the up direction is the driving force, m r omega squared. You have a Vmax, but the second it goes around a tight radius, this goes sky high, and this can this can get bigger when radius gets smaller. That's the most of the thing. If this gets smaller, this will get bigger force. So you can, because this is squared. So yeah, then you'll get a mold effect. Holy, I swear that puts this to bed. And I still think it might be shorter than some of the videos. It's just mind-numbing being on the bottom of the totem pole. You know what I mean? Yeah, there's nothing. I don't like to do this more than like once every month or so. And I threw in the towel. I thought it was already put to bed, that it was just a dumb idea. I mean, it's just like, why does a bike stay upright? That's literally the next one I should do, because that's the next one that just drives me insane. The fundamentals of why a bike stays upright are more in these majors. You know what I mean? You got to point out the major things, and not just be like, oh, it's got some trail. See that distance right there? That's the dumbest thing. I think this is a trap. Just like, and I'm not blaming Steve Mould, but just the whole jumping beans, 2 little jumping beans jumping off, and then measuring a force, and then just reiterating. That was the crazy thing. Measuring a force right here on the bucket, and then just instantly, just more magic beans, and it just made no sense, and it drove me insane, you know, to me. And I think it's hard to call out, and I will only call it out on a couple of occasions. And we're doing comedy, but holy, I don't mind getting a little bit heady. But anyway, yeah. For whatever reason, this one's just passionate too, because yeah. Anyway, okay. Well, thanks for joining me, and maybe we'll end with this. Hell yeah. Maybe we'll just end with this. Super loud, but it's fun. It's fun. It's not tall, you know what I mean? It doesn't jump up super tall, but there you go. You get a jump up. Alright, hell yeah. Alright, and then, yeah, it doesn't have to be called something different. It just has to be, yeah, it can still be called the Mould Effect. I haven't come up with a better name. Hell yeah. Alright, well, thanks for joining me, and guess what? That's a video.